Perhaps I ought to start. A student asked a question at the end of last time about when we do rotations, the generator is angular momentum. And angular momentum happens to be the momentum conjugate to the azimuthal angle. Is that just a coincidence? Can you guarantee in general that if we do a translation in a generalized coordinate, say capital X, right? In that case, it would be the azimuthal angle phi. Can we guarantee that the corresponding generator is the conjugate momentum, say capital P? I gave an answer last time by writing on the board, but because it was spontaneous, I don't think it was very systematic, and I don't think all of you actually caught what the issue was or what the derivation was. So I have written up just a couple of pages of notes to explain this issue. Those notes are posted on the website for this course. And I thought I would go through this very quickly now. But since the student who asked this question is not yet here, I will skip this first, and I just go back to the normal lectures. Maybe at the end of the class, if he's here, I will come back to this. All right? But in any case, you should try to download that page and read it yourself. Okay? So let me just skip this for the moment. And come to lecture 8, which is a slightly more detailed discussion of some of these, shall we say, technology related to the rotation group, and in particular its representations. I don't actually have time to go into applications, but I think I should start off with a bit of motivation, because this is mostly mathematical technology, all right, developing some tools. But why do you want those tools? And I would just want to give a couple of examples of problems in physics that are related to this set of mathematical tools. And just two examples. There are loads of other examples. The first example you actually know very well. Suppose you take the spectrum of hydrogen, right? So you have a 2p state. So, and there is, of course, you know, there is a 1s down here somewhere, and so on. If you apply a magnetic field, the 2p states split into 3, right? I guess that's called the Zeeman effect or something. So there are 3 states with m equals 1, 0, and minus 1. That you know very well, all right? So let me try to represent that in this way. So there are 3 states. I write the third one as a question mark for a reason that I will explain later. And they have these different values of m. So the first question you may ask is, why 3? Why not 4? Why not 10? Right? And suppose in an experiment, somehow you measure just the first 2. Can you then predict that there is a third one? And what its energy is? Okay? Why does it come in a set of 3? So that is a phenomena that you are familiar with. Historically, of course, people saw the 3 first before they understood the quantum number m. But if you try to imagine it in reverse, if the experiment came later, can you use some theoretical understanding about groups to relate the 3, to understand that there should be 3 and not 10, and so on? Okay? And in fact, this reverse argument happened in another example in elementary particles, where the group is not rotations, but SU3, which we shall explain later. Now, it turns out that in, I guess, the early 1960s, certain particles were found. These are, you may say, excited states of protons and neutrons, all right? And they were organized into a triangular pattern like this. There are 4 particles with charges +2, +1, 0, and -1. These are called the delta resonances, capital delta. Another set of 3, another set of 2. And these 4 has a strangeness 0, -1, -2. So that was the situation. People put them in a pattern like this. But basically, by using group theory, the group theory of SU3, Gell-Mann proposed that they should form a group of 10. Right? The technical term is called decouplet. Decouplet is just Greek for 10. So it's a pattern of 10, and he predicted there should be another one here. Okay? This particle is called omega minus, and the discovery of omega minus was a very important milestone in the use of group theory in elementary particle physics, in predicting the existence of a particle, and now also in predicting what its mass ought to be, to a very good approximation. And interestingly enough, it was at a conference, two papers were presented. Gelman presented the theoretical prediction, and the experimentalists, sort of, I think, on the same day, presented the experimental discovery, unknown to each other beforehand. And the experimental discovery, the experimentalists didn't know that it actually fitted into this pattern in this picture. Okay? Of course, in those days, there was no internet communication, so people actually go to conferences, and that's the first time they actually have a chance to talk to each other. Right? So this is actually an irreducible representation of the group SU3. Okay? A representation, I will give a precise mathematical definition later. For the present purpose, just heuristically, just a group of states that are deeply related. Okay? So this group of 3 is deeply related. This group of 10 is deeply related to each other. So that is the reason, some of the physical motivation why we want to study representations of continuous groups. Okay? And today we will use the rotation group as an example to study some of this. Now, some of the mathematics I have already assigned as homework. You have done it. So I will, again, go through it rather quickly, because the reason I assigned it beforehand is that I don't want to spend too much time doing arithmetic in class. That's not the point. Okay. So that's by way of preamble. So what I will talk about in terms of the rotation group is the idea of representations, the idea of irreducible representations, and to actually, for the case of SU2, it's actually quite easy. We shall be able to characterize all the irreducible representations. All right? So that's always a mathematical task. Given a continuous group, a Lie group, how do you characterize all possible irreducible representations? And I will spend a little bit of time on the smallest representation, which you will know, and then say a few words about other representations. Okay. And in this lecture, for the most part, I will use h bar equal to 1, just to save some writing. All right? So let me start with the idea of representations. From the last lecture, we talked about rotation. So if I rotate by some angle theta, theta is a vector. All right? So that shows the axis of rotation and the magnitude of rotation. That can be represented as an operator, which I write g of theta, acting on a wave function. Right? And that gives you the new wave function psi bar. And the rotation operator can be written as an exponential involving the angular momentum operator. So theta dot j. Theta is a parameter, j is an operator. And j, the vector operator, is a vector sum of 3 components, jx, jy, jz. And so g, whether you talk about g or whether you talk about j, they are operators. And j has that explicit form involving x, y, z, and the derivatives. Okay? Just to remind you, j operating on a function, you can calculate quite easily. Right? If I give you a function, j operating on it, you just differentiate and so on. Right? Differentiate with respect to y, multiply with respect to x. G is more difficult because it is exponential of something with a derivative on top. Right? So e to the derivative something. Okay? What do you mean by e to a derivative? Well, the only thing you can possibly mean is the infinite series. Okay? So that's, in general, that is something that's very difficult to calculate. Right? So suppose I ask you to calculate something like this. I give you a function of r, and I ask you to calculate even this, x dy minus y dx times some angle theta, let's say. It's actually rather difficult to calculate because you have to expand. And if it's just a derivative, it's a simple Taylor series, and that's just a linear displacement. But if it's something like this, it's actually rather difficult to calculate. Okay? So that's where we start. Now, suppose I have an n-dimensional subspace of functions. What do I mean? You know, in this example, hydrogen atom you can solve, right? So this is a wave function, this is a wave function, this is a wave function. You can write out what these 3 wave functions are, right? That's a standard problem in quantum mechanics. You solve for the P equals 1, L equals 1, M equals 1, 0, minus 1. You have 3 wave functions. Right? So it's a standard problem in quantum mechanics. So n is equal to 3 in this example. What do I mean by the subspace? That means any linear combination of these three. That forms a subspace of 3 dimensions, right? That's a linear space of 3 dimensions because it's a linear combination of 3 independent functions. And therefore, I have a certain set of basis vectors, psi 1 to psi n, namely the wave functions for this one, and this one. All right, so these are basis functions. And although I didn't write it down implicitly, I will always choose the basis functions to be orthonormal. All right, under some standard inner product. All right. Now, that's just a subspace. But let me assume that the subspace is closed under rotations. Now, what do I mean by closed? That means if I perform a rotation operation, in other words, operate on it by any g of theta, the end result stays in that subspace. Okay? The end result is still an element of this space. So, for example, if you have 3 wave functions, x, y, and z, if I do a 90-degree rotation, x may become y. So it stays within that set. Okay? So that is, if it happens like this for every possible rotation, that subspace is said to be closed. Suppose I only take x and z and not y. That's a 2-dimensional subspace. Right? So the functions would be a linear combination of x and z. That is not closed because when I rotate, I will get some y. That I will go outside the subspace. Then it is not a closed subspace. Is that okay? That's the definition of closed. Now, if it is closed, then if I operate on, say, basis function I, so that's the left-hand side, all right? So if I use a rotation operator operating on basis function I, the end result is still in that subspace, therefore can be written as a linear combination of all the basis vectors. So the linear combination, I just write the coefficient as this bracket g, I, j, psi, j. Of course, I mean sum over j, summation convention over j. Because it is closed, because this is a complete set of basis vectors for that subspace, this result can be written as a sum with these coefficients. These coefficients carry 2 indices, I, j, and therefore, together, they form an n by n matrix. Is that okay? So within a representation, within such a closed subspace, the abstract operator on the left-hand side, which I call G, just abstract operator, something like this, right? The derivatives and so on, can be identified with a matrix on the right-hand side. Now, the matrix has no operators, no derivatives, okay? They are just numbers. Because the end result of that operation could be, say, 3 times the first wave function plus 4 times the second wave function. So the elements G, I, J would be simply numbers. In quantum mechanics, they could be complex numbers. But they are numbers, not operators. Okay? So the idea is that in a closed subspace, abstract operators can be thought of as simply matrices, finite matrices. Okay? And this is then called a representation of the rotation group. And the idea is the following. Matrices are, of course, much easier to handle. You can do computations explicitly, right? If you want to multiply 2 matrices, you want to do commutator of 2 matrices, everything is okay. And the idea of the representation is that there is this one-to-one correspondence. If the operators obey certain commutation relations, then the corresponding matrices will also obey the same commutation relations, and so on. Okay? And it is much easier to study matrices than to study abstract operators. So that is the idea of representations. Actually, mathematicians distinguish between infinite dimensional representations and finite dimensional representations. Now, in physics, most of the time, 99% of the time, we worry about only finite dimensional representations. So n, for us in this course, will always be a finite number. In fact, typically quite small, like 3, like 10, all right? Now, the rotation operators g of theta would be the space would be closed under such a rotation operator if and only if the j's, in other words, the generators, are closed. They are closed under the generators. Why? Because you have something like this. The G is something like e to, I'm just writing abstractly, all right, schematically like this. So this is like, so if every time a J hitting a wave function, the result is still in that subspace, then you hit it twice, J square, still in that subspace, hit it 3 times, J cube is in that subspace, so the end result of the exponential is still in that subspace. Right? So it's easy to see that a space is closed under the rotation operators if and only if it is closed under the infinitesimal generators. And therefore, I can do the same thing with the J's. So any J, now A, the index A will always denote X, Y, Z. Any operator J acting on the state psi, I, is a linear combination of all the other basis functions with these coefficients. So these coefficients, again, are n by n matrices. Now, notice the indices. The indices A, B, C ranges from 1, 2, and 3. That is X, Y, Z. Whereas I, J, K will be 1 to n. N can be anything. Okay? And this is then called a representation of the corresponding algebra. Okay? The G are elements of the group. They multiply. The J's are elements of the algebra. They add, they commute, and so on. Okay? Now, it's obvious that it is easier to study the J's rather than the G. Okay? And actually, once you have a representation, this abstract relation becomes a matrix equation. That is, J, X, J, Y, J, Z are all n by n matrices. So on the right-hand side, you exponentiate a matrix. You don't exponentiate an abstract operator. Okay? And the left-hand side is another matrix. So this is a matrix relationship. Or, in fact, all relationships, all equations become matrix equations. So the question then is, what are all possible finite representations of the rotation group? This is something I will try to derive. Okay? And it is much easier to deal with the J's. I will deal with the J's, okay, and not deal with the G, because the answer is the same. Okay? Now let me start with some examples before I do the abstract theory. Okay? Let me take these 6 functions. So n is equal to 6 in this example. All right? 6 functions, x squared, y squared, z squared, and so on. So, and in fact, of course, the linear combinations of these functions. So this forms a 6-dimensional space. In fact, I can multiply by any function of the radius r, because under rotations, a function of the radius alone is unchanged. Now, I claim that this forms a 6-dimensional representation. How do you know? Well, there are 2 possible arguments. The first argument looks at it from the physical point of view. In fact, looking at it from the point of view of the G's. Because what is G? G is to rotate the function, right? When you rotate a function, if you start with, say, x, it becomes a linear combination of x, y, and z, right? So if you have any one of the, or a factor like x or y or z, it becomes a linear function of all the others. So if I start with a quadratic function, 2 powers, then no matter how I rotate, the end result is still a quadratic function. That could become very complicated. X squared could then involve xy, xz, and so on. But it must stay quadratic. Right? And here I have written down the space of all possible quadratic functions. Therefore, it must stay in that space. Right? Under rotation, a quadratic cannot become a cubic, cannot become a linear function. So it's under rotations, the space must be closed. Okay? Now, the other argument looks at it from the point of view of the generators. A generator J looks like this, right? It's a coordinate times a derivative. Schematically, I don't need to write down which component it is. A derivative will lower the polynomial order by 1, and then you multiply by x, you bring it back by 1. So J obviously turns a quadratic into a quadratic. Okay? So that shows this is, again, a closed subspace. Obviously, this argument means, now I have found a 6-dimensional representation. You can easily imagine, if you talk about cubics, you will have a higher dimensional representation. What dimension would it be? Well, you can count how many independent terms you can form with a cubic, all right? So obviously much larger, okay? So you can easily generate much larger dimensional representations. If you talk about things with power 15, that would be a pretty large dimensional representation. Okay. Now, let me organize these 6 functions into a particular way. I talk about x squared, y squared, z squared, and then the cross terms. I do a change of basis, basically, all right? The change of basis is the following. Let me take psi 1 to be x squared plus y squared plus z squared. And then the others, now 4, 5, 6 are the old ones, but 2 and 3 are chosen in such a way that the sum of the coefficients is 0. Oh, sorry, I goofed. Sorry, psi 3 is not correct. It's not x squared plus z squared, y squared plus z squared. Should be minus 2. Should be minus 2 here. And then I need to normalize these. I haven't told you about normalization. I want the sum of the coefficients to be 0 for 2 and 3, okay? So this is 1 minus 1, 1 plus 1 minus 2. There should be a 2 here, okay? So that's just a change of basis, right? So in the space of quadratic functions, I can represent any one of them as linear combinations of these 6. Now, why do I choose it in this way? The reason is the following. Let me just give 1/2 of the answer first, and then I will give the other half more systematically. Just think about rotations. If I do a rotation on psi 1, the result is just psi 1. Because psi 1 is just r squared. Under rotation, r does not change, right? X squared plus y squared plus z squared is an invariant under rotations. So although you have 6 functions, in principle, you take any one, you rotate, you get a linear combination of the others. Psi 1 is a particular simple one. It does not mix. All right? And the idea is that this 6 breaks up into 1 plus 5. If you rotate, psi 1 stays in psi 1. If I rotate any linear combination of 2 to 5, it becomes a linear combination of 2 to 5. Does not involve psi 1. Okay, now, the first half is that I rotate psi 1 does not involve 2 to 6. That argument is easy. I have already given you the argument, right? The reverse argument is slightly more complicated. That if I start with a linear combination of 2 to 6 and rotate, the result can be expressed as a linear combination of 2 to 6 without psi 1. That means, if this is true, that means the 6-dimensional space you can think of as a 1-dimensional space and a 5-dimensional space which have nothing to do with each other. They can be broken up into 1 plus 5 in this sense. They have nothing to do with each other in the sense that they do not mix under rotations. Now, let me give you the second half of this argument, okay? So under a rotation, you know psi 1 go into psi 1, does not mix 2 to 6. And conversely, the 2 to 6 only mix among themselves, do not mix with psi 1. So I want now to prove the second statement. Now, any of the quadratics can be written in the form in the first line as Sij, Ri, Rj. Now, Rij just simply means x, y, z. R1, R2, R3, x, y, z. Sij are just the coefficients. Okay? So if you have x squared, that means S11 is equal to 1. All the others are 0. Is that okay? So that's the most general way of writing a quadratic in terms of the coefficients Sij. Okay, so under a rotation, what happens? Under a rotation, you know that Ri becomes capital Rim, Rm, where capital R is the rotation matrix, right? That is what happened. This has nothing to do with quantum mechanics or anything. It's just when you rotate something, it becomes a linear combination, and the linear combination is represented by rotation matrix. Okay? So, and this R becomes Rj and Rn. I sort this out. I pull the two R's at the end. This Rim, I write as R transpose Mi, and then Sij, and then Rjm. I write it in this way because that ensures the repeated indices are right next to each other. And of course, by the rule of matrix multiplication, that is just the Mn element of the matrix product R transpose Sr. Okay? So let me call that square bracket S prime. So I'm just saying, under a rotation, the thing with S becomes the corresponding thing with S prime. You just change the coefficients. Okay? And S prime is given by R transpose SR. Okay? But let me look at the trace of the coefficient matrix. If I look at the trace of this thing, it is the trace of this. But you know the trace of a product, I can permute the elements. Right? The trace of ABC is the same as trace of BCA. That's a standard theorem. Okay? So if I just permute the order, I guess SRR transpose. But a rotation matrix must be orthogonal. In other words, R times R transpose is identity. So the trace of S prime is the same as trace of S. So this theorem simply says, forget about the details. I mean, just have to remember the main idea, that a quadratic function can be represented by a coefficient matrix S. Secondly, under a rotation, the trace of the coefficient matrix is preserved. But you see, functions 2 to 6 have zero trace. Because if I represent it as a coefficient matrix, the off-diagonal element, say xz, that would be this function. Let's say this function xz would correspond to S is equal to something like this. Xz would be maybe 1/2. Okay? This one. So it's only the 1,3 element. Okay? So that is, of course, a traceless matrix. For functions 2 to 6, I have chosen the sum of the diagonal elements to be 0. So that's a traceless matrix. So the traceless property is preserved. So if I start in the space spanned by 2 to 6, the result of a rotation stays in that subspace. Okay, so that proves the statement that 2 to 6 forms a totally independent subspace. So I've shown you two examples. Psi 1 corresponds to this matrix. Psi 2 corresponds to this matrix. So this has non-zero trace, this has zero trace. Okay? So when there is no mixing, that means if I work in this 6-dimensional subspace, everything is represented by a 6x6 matrix, then all these matrices break up into block form as a 1x1 matrix, a 5x5 matrix, and 0. That means they do not mix. Okay? A representation such as this, where the generators or the rotation operators break up into block form, is called a reducible representation. 可约. And if it cannot be broken, cannot be further broken. In fact, in this example, the 5 times 5 cannot be further broken. Now, how do you prove this? That's a separate issue. If it cannot be broken up, then it's said to be irreducible. 不可约. Right? Obviously, all we need to do is to find all the irreducible representations. Because all the reducible representations are just made up of irreducible blocks. Okay? And therefore, mathematicians always ask the question, what are all the possible irreducible representations of a group? Because it's the smallest building block. Okay? Now, in this example, this is actually an irreducible representation. Okay? Now, that is not a representation. Okay? So that leads us to the main question we want to deal with today, what are the irreducible representations of the rotation group. Okay. Now, let's imagine the following. I have skipped some rather obvious things, but let me perhaps write something. Suppose I have an n-dimensional subspace, which is closed. Okay? So all the J's are now represented as n by n matrices. Let's see what conclusions we can draw. So J square is an n by n matrix. Right? Now, my notation, I will from now on be rather loose. All the same symbol, very often I will use both to denote the abstract operator and to denote the corresponding matrix. Okay? So J square is an n by n matrix. It is Hermitian. Okay? So it can be diagonalized, right? Standard theorem. So J square can be written as a diagonal matrix. I can go to a basis within this subspace where J square is diagonal. So J square, then operating on any state, I can write as lambda operating on the same state. Okay? So that is the notation. If it's diagonal, it must have eigenvalues. The eigenvalues I call lambda. And the ket vector with lambda, that just means the corresponding state. The state with eigenvalue lambda is written like this. Okay? All the states with the same eigenvalue lambda forms a subspace. Because why? Because all the J's, JA, JB, JX, JY, JZ, commute with J square, right? Commute with J square. So, if let me do this like this. If I operate on this, what is JZ of this state? Well, because it can be commuted, this is equal to JZ operating on this state and then JX. But JZ operating on that state just gives you lambda. So you get lambda times the same state. Right? So a state with eigenvalue lambda, when operated by any of the J's, will give another state also of eigenvalue lambda. Okay? So those with the same value lambda is closed under all rotations. Right? So that is statement number one. So if I look at this subspace, all the states with the same value of lambda, within that state, that means if I have a space with different values of lambda, let's say I have 8 states, one with a value of lambda 1, one with value of lambda 2, then that is a reducible representation, right? Because all those with lambda 1 are independently closed, all those with lambda 2 are independently closed. Okay? So my irreducible representation can only have one value of lambda. That's the first thing. So I now assume I have only one value of lambda in that subspace. In that subspace, JZ is again a Hermitian operator. Therefore, it can be diagonalized. Okay? So if I operate on JZ, so within this space, I can always choose the basis such that JZ also gives just a number. Because it's diagonalized, M are the eigenvalues. So combining these two statements, that means that all the states have simultaneous eigenvalues, lambda and M. Okay? So a state will be labeled by lambda M, where lambda is the eigenvalue of J square and M is the eigenvalue of JZ. Now, a crucial property is that all the J's commute. Oh, sorry, I goofed. Here I'm in J square. Here I'm in J square. all the j's commute with j squared. That is something we proved last time. Okay? So it is possible to label states with two simultaneous eigenvalues. Now, you may ask, can I also have an eigenvalue of jx, for example? And the answer is no, because jx and jz do not commute. If two operators do not commute, you cannot have simultaneous eigenvalues. You cannot have a state which is an eigenvector of both operators. Right? In general, there may be exceptions. Okay? Therefore, the question that we are trying to answer, namely what are all possible irreducible representations, now becomes a much simpler and more concrete one, namely what are the allowed values of lambda and m. If I find out all possible allowed values of lambda and m, then I have answered this question. Okay? Now, just to remind you, this is the sort of argument you have to go through to construct all possible irreducible representations. Okay? The first step is to find the maximal set of commuting operators, all the commuting operators you can construct. In the case of rotation, it is j squared and one of the j components, which by convention is usually chosen to be jz. In other more complicated groups, there may be more than two. So you just find the maximal set of commuting operators. Then if there are, say, 5 of them, then you have 5 simultaneous eigenvalues, lambda, m, blah, 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 5 of them. And you ask, what are the possible values and relationship among these numbers? Okay? And of course, we want to see how the different states are related to each other. So how do we do it? Well, the way to do it is always to start with a basic state, which is sometimes called a root state. Say, suppose you don't know what are the others. You only know there is this one. Okay? So that is the root state. If you know there is one state, it's a root state, then you keep applying the j's. And you may get new ones, right? The first, you start with 1, you apply a j, you get another state. So that is a 2-dimensional subspace. You apply j again, you get a third state. You apply j again, the result does not give you a 4-dimension. It is still the linear combination of the original 3. Right? Then you get a 3-dimensional subspace. Right? So you keep applying the j's and see how much you get. The sum total of all you get must be a representation. Okay? So that is a representation. So let's deal with several theorems. The first I have actually used implicitly. The first theorem is that all the states in an irreducible representation must have the same value of lambda. Lambda is the same within an irreducible representation. Now, how do I know this? Suppose I start with the root state psi, and I apply a bunch of j's. I don't know how many, it doesn't matter, right? 50 of them in any order. And the product I call P. The result is psi prime. Well, let's see what happens. If I take j squared operating on the new state, then it is j squared P times the original state. But j squared commutes with every j, right? So I move the j squared past the first factor, past the second factor, and all the way. So it commutes with the whole P. So it is pj squared. But I assumed that this one has an eigenvalue lambda. The first one, the root state, has an eigenvalue lambda. So j squared operating on it becomes this number. Because it's a number, it can be pulled in front. And P times psi is psi bar. So that proves j squared operating on psi prime again gives lambda times psi prime. Okay? That proves every state in the same irreducible representation must have the same value lambda. Okay? Therefore, the states in the irreducible representation can only differ in m, right? Because they are labeled by lambda and m. Lambda is the same, so they can only differ in m. So how are the m values related? Let's say, suppose you have 3 of them, right? Say M1, M2, M3. How are they related? Well, you actually, in this case, you know the answer. The m's can only differ by 1 unit, right? So let's try to prove this. Prove that they must differ by 1 unit. Okay. Now, for this purpose, it's convenient to define these 2 operators, J plus and J minus. And I won't go through details. You have worked out the commutators. So Jz with J plus commutators J plus, Jz with J minus is minus J minus. And J plus J minus commutator is 2 times Jz. Okay? So instead of using x, y, z, very often we use plus minus z. Right? And you will see that they are convenient in some cases. And the other identity that we need is J plus J minus J plus is twice Jx squared plus Jy squared. Right? Just work it out. I mean, that's straightforward algebra. Therefore, I can write J squared in this form. Okay? The first part is just Jx squared plus Jy squared. That's just a very convenient way to write it. Okay, that's just preliminary identities that we need. Now, the second theorem I want is that if I use J plus on a state with value m, the end result is a state with m value m plus 1. It increases the m value by 1. That's why we call it J plus. But of course, it need not be that state normalized. There could be a normalization factor, right? And that normalization factor I just denote by C plus of m. Okay? So I will claim that this is the case. I will prove it, that J plus operating on something just increases the m value by 1. Now, let's see how that can be proved. So you have J plus operating on this thing. I call the result psi prime. So let me call this psi prime. How do I know the end result has a value m plus 1? Well, I have to prove that Jz operating on that state is equal to m plus 1 operating on that state, right? That is what I need to prove. How do I prove this? Well, very easy. Because Jz operating on psi prime. What is psi prime? Psi prime is J plus operating on this. The trick is always very easy. You try to swap the order. So instead of Jz, J plus, you swap the order J plus Jz. The difference is the commutator, which is Jz, which is J plus. Okay, this is an identity we proved before. But Jz now, where is the cursor? Jz now stands right next to that state. And Jz operating on that state gives me m. Okay? The idea is to move Jz right next to the state, original state, then it can be turned into the number, the eigenvalue. So you get m plus 1. Where's the cursor? So you get m plus 1 times J plus this thing, and J plus this thing is just the psi prime. Okay? So that proves that this new state has eigenvalue m plus 1. Next, I want to determine the coefficient C plus. So I just start with the definition that, that J plus operating on the m state is the normalization factor times the m plus 1 state. I square both sides. That is, I multiply each thing by its own complex conjugate. Okay? So on this side, I multiply by the complex conjugate, I get this thing. Remember, the complex conjugate of J plus is J minus. Okay? Because J plus is Jx plus Ijy. So J plus dagger is this thing, dagger is Jx minus Ijy. J, X, Y, Z are Hermitian. J plus, J minus are not Hermitian. Okay? So this is the left-hand side. Is that okay? And the right-hand side would be C plus squared, and this thing is by assumption normalized. its own inner product with itself. Its norm is 1. Okay? Now, let me try to work this into a form such that I can evaluate this thing. Because j plus j minus and j minus j plus has a commutator equal to 2jz, so I can write j plus j minus as this. So if I add j minus j plus, then j plus j minus j plus is 2 such factors plus 2jz. So I have the factor j minus j plus here is 1/2 the symmetrized form minus jz. Okay? I write it as the symmetrized form minus jz. But by the previous identity, the symmetrized form is just jx squared plus jy squared. Or in other words, it is j squared minus jz squared. So this operator can be written as j squared minus jz squared minus jz. Now, what's the idea? I mean, never mind the details of the algebra. You want to express it in terms of operators that you know about. Because I know what happens when I operate with j squared. I know what happens when I operate with jz. They give the respective eigenvalues. Okay? So everything else I try to express in terms of these. That's the whole idea. Okay? So this object I express in terms of things that I know. So put in here, I have this matrix element is equal to c plus m squared. So I get this. But you see, every time j squared operating on this gives me lambda, jz operating gives me m. So I get c plus square is equal to this thing. So I have evaluated the answer. Okay? Now, that only gives me the magnitude of this factor. The phase is purely a matter of convention, because suppose I have 3 states, I can always rotate one of them, the phase, by any angle, right? That does not change anything. If I rotate the phase of, relative phase of some of them, that would change the phase of C+. So I am free to choose the phase of C+ any way I want. That only establishes a relative phase convention for the wave functions in the basis. Okay? So I calculate the magnitude, I choose the eigenvalue, I choose the phase. So I have proved that, the first one I have proved exactly, that J plus is this normalization, oh sorry, mistake. When you check all them, there should be a square root here, obviously. There should be a square root to this factor, because what I calculated was the square. It's this square root times the next state, the higher state. And if you go through the same calculation with J minus, I won't go through, it's the same idea. You get a similar expression, of course, square root with a minus sign here. Okay? So, we now have proved, including this normalization factor, that whenever you operate with J plus, you increase the m value by 1. You operate with J minus, you decrease the m value by 1. You operate with Jz, the m value stays the same. Okay? And x and y is just a combination of plus and minus. So you operate with Jx is a linear combination of plus 1 and minus 1. So, next question. If the m values differ by 1, can you have m equals, say, 0.7, 1.7, 2.7, 3.7? These differ by 1, right? This is allowed by the results we have derived so far. But actually, you know that cannot be the case. So I need another result. Suppose I have a finite dimensional representation. Now, infinite dimensional representation, I won't bother. If it's a finite representation, there must be a lowest m and the highest m, right? Because if you keep going, if you can go all the way up and down, that would be an infinite dimensional representation. So let me call the lowest one, the m value, let me call it minus m1. So minus 0.7, is that possible? Well, let's operate with J minus. J minus is this coefficient, again I missed the square root, multiplied by m minus 1. So in general, you would get the lower one, unless the prefactor is 0. Okay? Now this is a general M, sorry. But if I use the M with the lowest possible value, then this square bracket becomes this square bracket, gives the lower state. You would then get a lower state, even lower than minus M1, unless this prefactor is 0. Okay? Because our general theorem is that every time you use J minus, you get the lower state with a coefficient. The only way you can stop in the process without going to minus infinity is when the coefficient becomes 0. So apply to the lowest possible state, this square bracket, I missed the square root, must be related to lambda like this. Okay? The lower state must be minus M1, where M1 is related to lambda like this. That actually, so if lambda is given, if you know lambda, then there are two possible values for M1, because this is just a quadratic equation for M1. Likewise, you can make the same argument for the highest possible state, which I call plus M2. And of course, the condition is that if I apply J plus to this state, try to go up, I must get 0. Okay? And that gives you a similar condition that lambda is M2 plus 1. Now, actually, the two equations are the same. Right? If you go back, lambda is M1 plus 1. Lambda is equal to M2 plus 1. So M1, M2 are the two roots of the equation lambda equal to x plus 1. This is a quadratic equation for x. There are two solutions. All right? And M1 and M2 are the two solutions. Actually, they are the two positive solutions. Doesn't matter. And in fact, they are the same. Because of the notation I use. I said the lowest one is minus M1. Okay? And the other one is plus M2. So in fact, they must be the same. Okay? And let me call both of them L. All right, from now on. So we have obtained the result that the lowest M is minus L. The highest is plus L for some L. Okay? So it must be symmetric about the middle. The range of M's must go from minus L to L. And lambda will be written as L plus 1 because of this relationship. And in future, I will just change my notation. Instead of writing the state as lambda M, I will write as LM. That's a more conventional notation. So the eigenvalue of J squared will be L plus 1. The range of M goes from minus L to L. So the range is 2L steps, right? The highest minus the lowest is 2L. And 2L must be an integer. Why? Because I go from the lowest to the highest in steps of 1, right? Each time I increase the M by 1. So the total increase from the bottom to the top must be a multiple of 1. Okay? So that means the range 2L must be an integer. So L is either a half integer or an integer. And the multiplicity, that is how many states are there together, is 2L plus 1. Because from 1 to L is L of them, minus 1 to minus L is L of them, and then there is a 0. Okay? The multiplicity is just a number of states. So we have found all the irreducible representations, all the finite irreducible representations. They are characterized, first of all, by a value of lambda L, which could be a half, 1, 2/3, 3 halves, right? Integer or half integer. And then M ranges within that multiplet from minus L to L. Okay? So you actually know the results. I don't know whether you have previously seen this is a fairly rigorous proof that these are all the possible irreducible representations. And the example I gave you is, of course, L equals 1, right? From minus 1 to 1, minus 1, 0, 1. Any questions? So the summary is that the allowed states are labeled by LM. L is an integer or half integer, and M ranges from minus L to L by steps of 1, and the multiplicity is 2L plus 1. So let me spend a little bit of time on the smallest representation. Well, I said L is a half integer or an integer, so the smallest must be 1/2. So let me look at the representation with L equals 1/2. And in this case, L is typically written as S because that's physically related to spin. Okay? This is a two-dimensional representation because that's the multiplicity. Multiplicity is 2L plus 1. 2L plus 1 is 2, so there are only two states. Okay. So the value of J squared operating on any of these states is equal to lambda, which is L plus 1. In other words, 3/4. There are only two possible states. M can either be a half or minus a half. And very often we represent these as spin down and spin up. And since this is a two-dimensional space, I can write the first one as 0, 1, and the second one as 1, 0. That's just the basis vectors in 2 dimensions. Okay? Now, of course, you can change them around, doesn't matter. But that's a conventional representation. So let's see what happens. Jz operating on the down states gives you minus a half times the down state. Why? Because the down state, by definition, has m equals minus a half. Jz operating on the up state gives you plus 1/2, the up state. Okay? Because that's the m value. And if I write this in the component notation, the down state is 0, 1. The up state is 1, 0. So you have a 2 by 2 matrix operating on 0, 1 gives you this, operating on 1, 0 gives you this, and you just think about it. That tells you what the matrix is. Okay? And the matrix is this one. Because you just check it. Let me just do one. I hope I haven't goofed. Huh? Did I goof the minus sign? Oh, no, oh, sorry. This is minus. This is minus, of course. Okay, could you please correct it? So if I take 1/2, 0, 1, 0, 0, minus 1, let's say take the upper line, operating on the down state, 0, 1, and you just multiply out. It is 1/2. So this multiply gives 0, this multiplies it gives you minus 1, so this minus 1/2 times itself. Right? So if you know, because given any operator or matrix, if you know the result when it multiplies all the basis vectors, operates on all the basis vectors, then you know the whole matrix. Okay? So I can now read off the matrix Jz. Sorry about the minus sign. I also want to represent Jx and Jy. But it's always useful to start with J plus and J minus. J plus operating on the down state gives you the up state with that coefficient. I represent the down state as 0, 1, the up state as 1, 0. Here m is minus 1/2 because m is the m value of the guy you start with. And LL plus 1 is 3/4. So putting all this together, J plus operating on 0, 1 gives you 1, 0. And J plus operating on, I don't know whether I have, plus operating on this state, on 1, 0, of course, gives 0. Because if you take the up state and try to raise it one more, there is nowhere to go. You must get 0. So that shows that J plus must be this matrix. Okay? If you take this, you can easily check this expression. And these two 0 in the bottom row means if I hit it on the other state. Did I goof? No. See, this multiplied by 0, 1. That's correct. This operating by 1, 0. Yeah, this column being 1, 0 means when you hit 1, 0, you get 0. Okay? And by the same argument, I won't go through details, you find J minus has a 1 in the other corner. So I have found all three matrices. Okay? And since Jx and Jy are linear combinations of J plus and J minus, you find they are like this. Okay? By the way, check that they are Hermitian. Jx is real and symmetric. So that's Hermitian. Jy is imaginary and anti-symmetric. So that is also Hermitian. Okay? So I have written Jx, Jy, Jz, J square, all as 2 by 2 matrices. So that is everything you need to know in a representation. Any questions? So I have constructed the smallest representation. Okay? The construction, the end result, always means I am able to represent everything explicitly as matrices. In this case, they are very small matrices. By the way, just to give you the conventional statement, all the J's typically are written as 1/2 sigmas. Sigma is just that square matrix without the half, and the sigma satisfy these commutation relations. Commutator of 2 sigmas is twice the other sigma. Okay? And the sigmas are called Pauli matrices. That's just a matter of convention. Pauli started off without the factor of 2, that's all. Okay? Oh, by the way, we should check J square. Now, we say that J square must have 2 properties. It must have the same value when hitting all states, right? That means as a matrix, it must be the identity matrix, must be proportional to the identity matrix. Because it hit any state in the space, it must give a number, the same number times the same state, right? So it must be a number times the identity operator. And the number we know is just a value of lambda. In other words, L plus 1, in this case 3/4. So we have to check that J square in this subspace is 3/4 times the identity. Okay? And the way to do it, well, you have Jx squared, Jy squared, and Jz squared. Jx is this matrix times 1/2, and so on. So just write it out. Okay? So you have a bunch of 2 by 2 matrices. You just go do the calculation, and you find. Now, that is something, yeah. So you have 3 terms, each giving you 1/4 times the identity. So the answer is 3/4 times identity. So this is the matrix representation for J square in this representation. Okay? So in any of these representations, J square must be an identity, proportional to the identity. Now, this representation has something slightly strange and unexpected. Normally, when you say, I rotate by 2 pi, say about the z-axis. Let's be simple. Rotate about the z-axis by 2 pi. Well, should be the same as no rotation, right? Nothing has changed if you rotate by 2 pi. Let's see what happens in this case. If I rotate by 2 pi. Well, the general representation for a rotation operator is something like this. I'm using h bar equal to 0, equal to 1. And whether or not you put a minus sign here doesn't matter. Whether you do it clockwise or anti-clockwise doesn't matter. So theta is 2 pi. And I rotate about the z-axis. So it is Jz. Okay, so let's do this on the down state. So it's this operator operating on the down state. Now, what does the exponential of Jz mean? Whether or not you use the matrix doesn't matter. It just means the power series for an exponential. So a power series, a typical term would have Jz to the nth power. Each time Jz hits the down state, it gives a factor of what? Minus 1/2, the eigenvalue, right? So if you have 2 factors, you take the first one, closest to the state, operate, turns that factor into minus 1/2, pull that factor out, then the next one. So every factor of Jz becomes a factor of minus 1/2. All right? So you collect everything back into the exponential. So it's the same as changing the operator in the exponential to minus 1/2. Is that okay? So, well, This is just a number. And what is this number? This number is -1, right? Because it's e to the minus pi times I. So if I rotate by 360 degrees, the wave function does not return to itself. Returns to minus itself. Okay? Is there any problem with that? No, because what we detect is the probability square, right? The phase of the wave function has no physical meaning. Okay? Now, if you demand that when you rotate back to itself, you get the same answer without a phase change, then there would be no possibility of spin a half. Perhaps okay, the final statement. Suppose you look at this kind of wave function, which you get by solving Schrödinger's equation. They are functions of position, right? So they are functions of x, y, z. If you have functions of x, y, z, in other words, the only degree of freedom is position, then with x, y, z, if I turn by 360 degrees, doesn't change, right? If you take x, change by 360 degrees is x, not minus x. So all functions of position under 360 degree rotation returns to itself with a phase +1. So any spin a half, in fact any spin, half integer spin, 3 halves, 5 halves and so on, cannot be due to the position. Or in physical terms, it's not due to orbital angular momentum. It is something that has nothing to do with x, y, z. It is just the electron having its intrinsic spin. That intrinsic spin has nothing to do with any x, y, z. It's not because it has some internal structure and is rotating in some x, y, z. At least not in the Schrödinger representation. Okay? It's totally something totally unrelated to any kind of orbital motion because of this. Okay? Any questions? There is actually one more question that I have not answered, and I have actually not set it as a problem, and that is how to represent general rotation. Suppose I rotate by, say, pi over 3 about the x-axis. Okay? What is g? Well, g would then be e to the I pi over 3 sigma x over 2, right? Okay, because j is 1/2 sigma. So this would be e to the I pi over 6 sigma x. Okay, just an example. But this is a 2 by 2 matrix. How do I represent this matrix? In fact, you know something. These matrices, identity sigma x, sigma y, sigma z, any 2 by 2 matrix can be represented as a linear combination of these 4. Because there are only 4 independent 2 by 2 matrices, right? There are 4 entries. So this you must be able to express as a linear combination like this. Okay? So you must be able to express and in fact it's not necessarily pi over 6, any angle. Okay? So let me leave it as a challenge to you. Do this. And there are obvious generalizations, right? Does not have to be x, can be unit vector dot sigma. That is, can be about any direction. So the general challenge is to evaluate the following. E to the I theta n dot sigma. N is a unit vector represented by 3 cosines. Okay, it's a unit, well, by an angle. Well, let me not call this theta. Let me call this alpha. And n is a unit vector. Of course, the most general unit vector is like this: sine theta cosine phi I plus sine theta cosine phi sine phi j plus cosine theta k. Okay, it is a unit vector with polar coordinates theta and phi, so it's pointing in that direction. So I rotate by an angle alpha about this axis is represented by this operator. This operator must be expressible in this form, where the 4 question marks are just numbers, complex numbers, no more matrices, right? All the matrices are shown explicitly. Okay, so in any representation, there is still this further task of how you actually express the finite transformations in terms of matrices. Okay, what I did just now was an example where I rotate about z by 360 degrees. So the more general question is I rotate about any axis by any angle. What is the answer? Let me just give you a hint of what happens. If you take sigma x, you expand this. The answer is very simple, because sigma x squared is the identity. Okay, so all the even powers become identity. And all the odd powers, you have sigma x to the 7th power, the 6 powers become identity. So it becomes sigma x. Okay? So roughly speaking, this one you know quite well. Because if all the even powers, you look at it, that's just the cosine. The even powers of the exponential function is the cosine. So it's roughly cosine times identity plus I sine times sigma x. Okay? Something like this. But how about in general? I leave it for you to think about.
Let me add that this was a question in the most recent PhD qualifier exam.
Oh, I see.
If you want to do PhD here, you should know how to do it.
All right. So that was the smallest representation. So let me say something about the other representations. I deliberately use a slightly different technique to deal with it. Let's say L equals 1. Well, L equals 1 is like this. You can use the same idea that I used before to find out what they are. But let me do something, use a slightly different approach, just so that you learn about different ways of looking at the problem. And let me just say, suppose I have these 3 functions. X, y, z times some function of r. And let me just take it to be a Gaussian in r. Actually, any function of r is okay. And I just put that in so that I can normalize, right? Normalization just means the absolute squared volume integral, okay? So without the damping factor in r, I would not be able to do the volume integral. Now, this certainly forms a representation, right? Because if I rotate, then x, y, z under any rotation just become linear combination of x, y, z. The exponential factor is unchanged. And since there are 3 of them, you can easily guess, since the multiplicity is 3, and in general we say multiplicity is 2L plus 1, this should be the L equals 1 representation. Okay? The question I want to ask is the following. Because we now have 2 languages. One is an explicit functional form. The other is an, shall we say, a direct cat notation where I label by L and M. So all of them have L equals 1. They have M values 1, 0, and minus 1. So what is the relationship between this language and that language? Okay? So, for example, what is this state in terms of these? Well, let's try to look at it as follows. Take the state 1, 0. That is the state with M value equal to 0. It must be a linear combination of these 3 states, right? These 3 functions. So I write it as beta x times x plus beta y times y, and so on. That's the most general linear combination of the 3. So the question now becomes, can I determine the 3 betas? Okay. So that relates the abstract Hilbert space representation in terms of the ket vector to the coordinate space representation of the wave function. Now, we can't do this in the previous example because I showed spin 1/2 cannot be represented in terms of x, y, z, and so on. Okay? So the question is then to determine the betas. Now, this was actually set as a problem for you. So let's see how do we do it. Well, to say that it has m equals 0 means if I operate on this with jz, I get 0 times the same state, right? 0 times the same state is 0. That's just the m value. So I write out what jz is. Operating on this is 0. I substitute this wave function into here. So I convert, you see, this eigenvalue equation in matrix form or in ket form into a differential equation. That is the point I want to establish. All right? So we have something like this. In general, you have Jz Lm is equal to M Lm. Actually, we are trying to relate three ways of looking at this equation. We started off where Jz is an abstract operator. Okay? Then we turn Jz into a matrix. Now it's a 3 by 3 matrix. Now we go back to function space and represent Jz as this operator. So this equation, which looks kind of abstract, now becomes a differential equation. This is a differential equation. Okay? And you want to find the betas that allow this differential equation to be satisfied. So let's see. So I just demand this to be 0. And the dy, this term, operating on the x and z would give 0. Operating on the y would give 1. So this term would give x beta y. Likewise, this term would give y beta x. That has to be equal to 0. 0 as a function. So it's an identity in x, y, z. Okay? And that can only be true if beta x and beta y are both 0. So this wave function is just some number times the z component. And this number is determined by normalization. That is, this is equal to 1. Okay? And this does not equal to, need not be this. It can be any function of R. So that determines everything up to a phase, of course. You can never determine a phase. And by convention, you typically choose beta z to be real and positive. Okay, so that is, I establish a relationship between this abstract notation and an actual functional form. So I think this has been an exercise that has been assigned to you to find all three states. I just did the m equals 0, 1, including normalization. There are actually two ways of doing this. For example, if you want the one with m equals 1, I can apply j plus to this wave function. What is j plus? J plus would be some derivatives, right? X dy, that sort of thing. So you just apply x dy or whatever to this wave function. Okay? So that's the first way. The second way is to directly solve the partial differential equation. Say Jz operating on the one state gives you 1 times the same state. I think I have a slide. Oh, okay. So both ways should give you the same result. Any questions? I think I already set the problem with m equals 1 as well. This actually goes back to the example I started off earlier. I take the space of all quadratic functions times a Gaussian in R. These 6 functions clearly form a representation by the argument I gave earlier, because quadratics turn into quadratics under rotation. And we guess that the 6 must break up into 5 plus 1. Okay? And that I have actually told you earlier today. The 5 must correspond to L equals 2, because 5 is related to 2L plus 1. And the 1 must correspond to L equals 0. In other words, a D state and an S state. So as an example, you could try to do the following. Find the normalized wave functions for the 6 states in this form. L equals 2 any m, L equals 0, of course, m equal to 0. Okay? For example, what do I mean by the 2-2 state? L equals 2, m equals 2. It has to satisfy these equations. They are just differential equations. Okay? And you just write 6 coefficients and use these equations to determine the 6 coefficients. Any questions here? Yeah?
So the images being can be the same as the orbital.
Say that again?
You mean that half image spin not be as the
orbital, yeah.
XYZ?
Yeah.
Then
I wonder if integer spin can be
represented by...
same as the orbital rate.
Yes, there's an isomorphism. Now, mathematically, there's an isomorphism, meaning that structurally it is allowed. But physically, it does not have to be orbital momentum. You can have spin, integer spin. For example, you have two electrons, spin 1/2, and they have no orbital momentum. Obviously, they can combine to spin 1. So that's purely spin. Okay? So the exclusion goes only one way. Half integer cannot be orbital, but integer can be orbital or can be spin. And that really relates to the next question. How do you construct things out of spin 1/2 objects? That is a mathematical construction more than a physical one. If I start with spin 1/2, can I construct all the other spins? In other words, suppose I have spin 1. Can I think of it as 2 spin 1/2s put together? Right? Or spin 3/2. Can I think of it as 3 spin 1/2s put together? Now, this, I will just give a simple example here. I think I have just enough time. But this is an example of what is called multiplication of representations. Okay? 2 spin 1/2s combined, what do you get? Or 2 representations, 2 irreducible representations. You take what is called an exterior product. What do you get in the end? I won't give and that expansion has to do with what's called Clebsch-Gordan coefficients in the case of SU2. I will cover Clebsch-Gordan coefficients later. But this is the simplest possible example of something like this. So at least mathematically, we can regard all angular momentum as being made up of spin 1/2 objects. And everything can be built up from spin 1/2, mathematically. So let's try to do this, do the simplest possible example. So, and this actually is trying to set the scene for a future lecture when we come to isospins. Okay? So the spin up, I can write it either as 1, 0, or I simply call it U, spin up. And the other I call spin down, D, or you write arrow up, arrow down. Now, suppose I have 2 particles. That's what I mean by n equals 2, forming L equals 1. In other words, I try to do the following. I have these 4 states, right? Suppose, think of it physically. Think of these as electrons. First electron is either up or down. Second electron is either up or down. So when you have 2 electrons, there are 4 possible states. Either 2U, 2 up, up down, or down up, or down down. There are 4 states. Okay? And what I will show is that these 4 states can actually be broken up into 3 plus 1. 3 is an L plus 1 multiplet, L equals 1 multiplet, and the 1 is an L equals 0 multiplet. So what you have in terms of angular momentum is angular momentum 1/2. 2 angular momentum 1/2 combined is equal to angular momentum 1 and angular momentum 0. Okay? Sometimes mathematicians write a shorthand sort of like this, right? 2 angular momentum 1/2 objects combined together is actually either an angular momentum 1 object or an angular momentum 0 object, right? That's the decomposition. So if we want to understand this, we have to find out what happens if any of the J's hits any of these states. And to do this, all you need to know is the following, something like this. J minus turns a U to a D, okay? So J minus on UU, what happens? That's the rule you have to know. It separately operates on each of the 2 electrons. It's just like a differential operator when you operate on a product, right? You operate on the first factor and keep the second fixed. So if it operates on, say, the second factor, it gives UD. It operates on the first factor, it gives DU. Right? That's the only rule you have to know. So let me start with, whenever you do this, the trick is always to start with the state of highest M. Because if you have 2 electrons, spin 1/2, spin 1/2, what is the M value? Well, If this is spin up, m value is 1/2. This is spin up, m value is 1/2. When you combine, the highest possible m value is 1/2 plus 1/2 is equal to 1. Okay? So UU must correspond to the state with maximum m value, m equals 1. Do you understand? Now, m values are additive. Oh, this is another example of the same rule. Because if I take JZ operating on, say, UU, when it operates on the first factor, it gives 1/2. When it operates on the second factor, it gives 1/2 times the same thing. Right? So that means the total m value is additive for the two parts. Okay? So you see the total allowed m values are simply 1, 0, 0, minus 1. Okay? So m values is easy to sort out. So if the m value, the maximum is 1, then L is equal to 1. It cannot be L equals 2. Now, although you can have in principle a state L equals 2, m equals 1. But if you have such a state, there must also be an m equals 2, right? Because it's a representation. These four, no matter how you rotate, they are closed. But if you have an L equals 2, m equals 1, you rotate it in a certain way, you must get m equals 2. Okay? So if the range of m's maximum is 1, that must be L equals 1. So we identified the higher state. This is very easy. Okay? It's UU. But if I know this and I apply J minus, then I can find these two. Let me just do one for you. J minus L equals 1, m equals 1 is equal to J minus UU. On the left-hand side, I apply my usual rule that J minus operating on anything is L plus 1 minus m plus 1 or minus 1. Minus 1, I think. Minus 1. The lower m. Okay? You have a factor like this, right? You know what happens if J minus hits any one of these states. You reduce m by 1, and there is a prefactor that you know. On this side, I have already explained this is equal to ud plus du. Okay? And in fact, you work this out, I guarantee you this is square root 2. So I have the answer. That's the answer. Okay? Why do I know this is... I don't even have to work it out. I know this is square root 2. Because I know the thing must be normalized. Right? And if this combination is to be normalized, it must be 1 over square root 2. Right? Because the prefactor guaranteed was chosen to guarantee normalization. Now, so if you find this and you do it once more, you find the one with minus 1. Which must be, of course, just dd. The only question now you have to be very careful. It could be minus dd or I times dd. Right? You don't know the phase. But this whole thing, I have already established a phase convention. So the relative phase is determined. Now, how about this one? That accounts, this L equals 1 accounts for 3 states. There must be a fourth one. The fourth one must be L equals 0, m equals 0. Well, what can it be? If it's m equal to 0, it must be a linear combination of these two. Right? So L equals 0, m equals 0 must be a linear combination of these two if it has m equals 0. What linear combination? Well, it must be orthogonal to this one, right? So that gives you the condition to determine it up to a phase. And in fact, you can do it by inspection. It is 1 over square root 2 relative minus sign, okay? Because that's normalized, and you take the inner product of this with this, of course, you get 0. So the trick always is the following. You start with the largest possible m, that is easily read off. Then you use the lowering operator, J minus, to get the whole ladder. Then you use orthogonality to get the next lower L. Okay? Now, I will go through this later more systematically for something more complicated than this simplest case. This simplest case, as I said, is 1 half becomes 1 plus 0 schematically. Okay? You can do anything, you know. How about this? You go to what? What happens if you break this up? Okay? So L equals 3 plus L equals 2. Add together. What happens? This is called the problem addition of angular momentum. Okay? And in fact, I can tell you what this is. This is 5 plus 4 plus 3 plus 1. 3 plus 2 plus 1. Okay? So angular momentum 3. So if you have two objects, one with angular momentum 3, one with angular momentum 2, that forms a representation. That representation is broken up into the following irreducible representations, namely angular momentum 5, 4, 3, 2, 1. And let's check the multiplicity. Now, 3 has a multiplicity 2L plus 1 of 7, right? This has 2L plus 1 of 5. So the total number of states is 35. How about you check here? 2L plus 1 is 11. 2L plus 1 is 9, 7, 5, 3. Okay? Does it work out? 20. 33. Okay? So it works out exactly. Okay? Now, the fact that the multiplicity work out is a necessary condition. It's not a sufficient condition. Right? That's not a proof, but that's just a useful check. Right? So now, when you have two representations and I multiply them together, the end result is always a representation. Because, you see, if I do a rotation, this one stays within its original set. This one stays within its original set. So the product stays within the product set, right? So it is closed. So that's obviously a representation. But in general, it will not be an irreducible representation. So this problem is how you decompose product representations into irreducible representations. Okay? And what I have told you is the simplest possible case. A half actually breaks up into 1 and 0. And I think later, or perhaps you have already done this, there is a slightly more complicated example, just so that you know how it works, with the so-called Clebsch-Gordon coefficients. Okay, so that's it. Let me stop here. We still have a few minutes if you have questions. We are still one lecture ahead. Let me return to the remark I made at the beginning. One student who is not here today raised the question of what happens under generalized coordinates. How do you guarantee that translations in generalized coordinates, which includes the example of angle, is generated by the corresponding conjugate momentum? How do you guarantee this? And I have written up a set of notes that basically answers this question, not in the most general possible context, but general enough to be substantially non-trivial. And it's in the, on the course website, right? So you can download and look at it. And next time, I hope that student will be here next time. I will quickly go through it. It will only take us 15 minutes or so. Because it's actually a quite important problem that now tends not to be taught. Because even purely within the realm of classical mechanics, there is a theorem which is, at the end of the day, essentially the same idea. The theorem is that canonical Poisson brackets are invariant with respect to generalized coordinate transformations. Because you say a coordinate Poisson bracket with a corresponding momentum is 1, right? Now, if I do a generalized coordinate transformation, I know how the coordinates transform. I know how the momenta transform. Can you still guarantee the same thing happens under coordinate transformations? You see, this is a part of a general class of problems that we need to deal with. For example, you have a statement like this. For example, A dot B is equal to something. This is vector. Now, say A dot B equals 5. This statement is invariant with respect to Cartesian coordinate transformations. If I go from one Cartesian coordinate to another Cartesian coordinate, right, where dot I just means multiply x component, multiply y component, so on. So that is a statement that is invariant with respect to rotations. Now, in mechanics, you have classical mechanics, you have this statement. This is the classical Poisson bracket, right? The statement is this is invariant to general coordinate transformations. Does not have to be linear transformations, right? You change x to x squared, and so on, okay? The P is the corresponding P as defined by the Lagrangian. It's the conjugate momentum. That when you change coordinate, this statement remains valid, okay? And this is purely a theorem in classical mechanics, and this is essentially what's behind the question that was asked, okay? And in a set of notes, I basically gave a relatively simple and not too abstract proof of this result, even though I use quantum commutators, the same idea. Okay? So take a look at it, and we'll talk about this next time. Okay? Any other questions? Yeah?
How do you find the 5 bases of the subspace?
5?
I mean, 5, psi 1 to psi 5, psi 2 to psi 6.
Yeah?
I think it's hard to find the exact form.
No.
Where
No.
there's a systematic way to find that.
No. There are many possible representations. Suppose you have an L equals 2 representation. It could be x squared. I mean, it could be this. It could be this. What do you like? Could be this, right? That's also good. That's singular at the origin. But, right? Just using rotation group, you can't tell whether it's this or this. The radial function you can't determine.
I mean the 5 bases of the subspace.
How do you find it?
How to find? Yeah.
Oh, yeah. Now.
Because one is true quadratic, there are the 5, and one is maybe cubic form, one is 7, and the exact form, how to find it, is a systematic way.
Oh, yes. There is a systematic way in this case.
Is it related to Lagrange polynomial?
No. Lagrange polynomial is only function of one variable. This is function of 3 variables, x, y, z. I can tell you how to do it. In fact, the trick is to define x plus or r plus as x plus iy. Okay? Suppose you have a state L and the maximal m. Okay? This corresponds to the state r plus to the m power, r plus to the L power, times any function of r. Okay? So this is a rule that gives you the higher. Of course, there's a normalization factor. That gives you the first one, the highest one. And the others you can just keep lowering, use the lowering operator. Okay. Essentially, you see that the idea is very simple. X plus ry, if you go to polar coordinates, that is proportional to e to the I phi. Phi is the azimuthal angle. Because it's cosine phi, this is sine phi. Right? Never mind theta and so on. Just look at the phi dependence. So when you have L factors, this goes like e to the I L times phi. And Jz is essentially dd phi. Okay? So Jz operating on this state will give you L. Okay? Now, that does not answer the question for other groups, but for the rotation group, that basically gives you the answer. That the highest m is just given by the relevant factors of r plus times any function of r, which you cannot determine. That's just like when you solve a problem in quantum mechanics involving a spherically symmetric potential. The YLMs, of course, you determine. But the radial function depends on your potential. You cannot determine, right? And what we have done is essentially the YLMs, right? what we have discovered essentially the angular part, which is the YLMs. Oh, if I don't write it as quadratic, whenever you have a quadratic function, you always divide by r squared. Instead of x squared times something, I always divide by r squared. Then, and these, of course, are functions of the angles only, right? Then these are basically the YLMs, okay? So I haven't written down, but that's just convention. So the ones with x squared, y squared, and so on is just the Y2Ms, okay? And well, in fact, what the YLMs are by now, they are tables, right? So people have done it for you, but you need to learn the idea. You don't need to actually work it out for very large ones. It's tabulated. And of course, the theta dependence has to do with the Legendre polynomials in theta. Okay, so these are YLMs. YLMs are the well, strictly speaking, the associated Legendre polynomial times e to the im phi. That's what you get when you try to solve the Schrödinger equation or something like that in polar coordinates. You solve the angular part. Okay. But what I have tried to do is to present that part in algebraic notation. Okay. Anything else? Okay, let's end here. Right, still no homework. I think we have not yet come to anything beyond. Okay, thank you.